RS-28 Sarmat Satan Roman II. The science behind the world's most powerful ICBM. The physics of ultimate deterrence in the silent underground chambers of Russia's strategic missile complexes lies a weapon engineered not merely for war, but for deterrence on a planetary scale. Hidden beneath reinforced steel doors and layers of hardened concrete, the RS-28 Sarmat intercontinental ballistic missile represents the culmination of decades of rocket science, nuclear strategy, and advanced military engineering. First revealed publicly in the 2010s and entering testing phases leading toward operational deployment around 2023, the Sarmat missile is designed to replace the aging R-36M2 Voevoda, a Cold War-era heavy missile known in NATO terminology as Satan. The successor, often referred to in Western defense analysis as Satan Roman II, is not merely an upgrade, it is a fundamental leap forward in strategic missile technology. But to understand why the Sarmat missile matters, we must step into the deeper scientific principles behind intercontinental ballistic missiles, orbital mechanics, propulsion engineering, atmospheric reentry physics, and the complex mathematics of nuclear deterrence. Chapter 1: The science of intercontinental ballistic missiles. At its core, an intercontinental ballistic missile, or ICBM, is essentially a suborbital rocket system. Unlike cruise missiles that rely on sustained powered flight through the atmosphere, an ICBM launches into space, following a trajectory governed primarily by Newtonian physics and gravitational dynamics. The typical flight of an ICBM consists of three phases. 1. Boost phase. During the boost phase, the missile's powerful rocket engines accelerate the vehicle to velocities exceeding 7 kilometers per second. In this stage, the missile behaves similarly to a space launch vehicle. Liquid or solid rocket propellants combust in the engines, generating thrust according to Newton's third law of motion. The thrust equation governing rocket propulsion is F equals m times v, where F equals thrust force, m equals mass flow rate of exhaust, v equals exhaust velocity. The higher the exhaust velocity and propellant flow rate, the more powerful the rocket engine. For heavy ICBM like the Sarmat, enormous thrust is required because the missile must lift a payload mass that can exceed 10 metric tons, including nuclear warheads, guidance systems, decoys, and penetration aids. 2. Mid-course phase. Once the engines shut down, the missile enters the mid-course phase. This stage occurs outside Earth's atmosphere, typically reaching altitudes between 1,000 and 1,500 kilometers. At this point, the missile follows a ballistic trajectory, meaning its motion is governed purely by gravity and inertia. In physics terms, this path resembles a section of an elliptical orbit around Earth. During this phase, the missile's payload section releases multiple independently targetable reentry vehicles, or MIRV. These warheads separate and continue toward their targets along slightly different trajectories. 3. Terminal phase. As the warheads descend back into the atmosphere, they experience extreme thermal and mechanical stresses. At speeds exceeding Mach 20, the air in front of the warhead compresses violently, creating temperatures hotter than the surface of the sun. To survive this environment, reentry vehicles use advanced ablative heat shield materials. These materials absorb and dissipate heat by gradually vaporizing during atmospheric entry. Chapter 2: Development of the RS-28 Sarmat. The development of the RS-28 Sarmat began in the early 2000s as part of Russia's strategic modernization program. The project was led by the Makeyev Rocket Design Bureau, a Russian engineering organization with decades of experience designing submarine-launched and heavy strategic missiles. The motivation behind the program was simple but strategic. Many of Russia's Cold War-era heavy missiles were approaching the end of their service lives. The aging R-36M2 Voevoda system, despite being extremely powerful, required replacement. The new missile had to meet several demanding objectives: greater payload capacity, improved survivability against missile defense, extended range, faster boost phase compatibility with new hypersonic payload systems. These requirements pushed engineers to rethink many aspects of missile architecture. Chapter 3: Engineering. A 200-ton rocket weapon. The Sarmat missile is among the largest and heaviest ballistic missiles ever constructed. Approximate characteristics include length, around 35 meters, diameter, about 3 meters, launch mass, roughly 200 metric tons. To visualize the scale, the missile weighs roughly as much as 2 fully loaded Boeing 747 aircraft. Designing a rocket of this size introduces enormous structural challenges. The missile must withstand extreme vibration during launch, intense internal pressure in propellant tanks, aerodynamic forces during atmospheric ascent, shock waves from stage separation events, To manage these stresses, engineers use high-strength aerospace alloys and complex internal structural frames. Chapter 4 Propulsion System. Unlike many modern ICBM that use solid rocket motors, the Sarmat relies on liquid fuel propulsion. Liquid propulsion offers several advantages for heavy payload rockets. These include higher specific impulse, greater thrust control, larger payload capacity. Specific impulse, abbreviated ISP, measures rocket engine efficiency. It is defined as the amount of thrust produced per unit of propellant consumed. Mathematically, ISP equals thrust/propellant weight flow rate. Higher specific impulse means the engine can produce more thrust for longer durations. Russian heavy missile designs have historically favored liquid propellants such as Udman symmetrical dimethyl hydrazine and nitrogen tetroxide oxidizer. These propellants ignite spontaneously when combined, eliminating the need for complex ignition systems. However, they are also highly toxic and require specialized fueling infrastructure. Chapter 5 Global Range Capability. One of the defining features of the Sarmat missile is its extraordinary range, estimated at approximately 18,000 kilometers. For comparison, Earth's circumference is roughly 40,075 kilometers. This means the missile can theoretically strike targets on nearly any continent using a wide variety of trajectories. Traditional ICBM routes between Russia and North America travel over the North Pole, which represents the shortest path due to Earth's spherical geometry. However, the Sarmat missile is reportedly capable of using southern orbital trajectories, approaching targets from unexpected directions. This complicates missile defense planning, because most early warning radar systems are optimized to detect northern trajectories. Chapter 6 MIRV Technology. Perhaps the most strategically significant capability of the Sarmat missile is its ability to carry multiple independently targetable reentry vehicles, or MIRV. Instead of delivering a single warhead, the missile can deploy multiple warheads that separate during the mid-course phase. Each warhead can then strike a different target. This dramatically multiplies the destructive potential of a single missile. A single Sarmat launch may deploy up to 10-15 nuclear warheads, depending on payload configuration. Each warhead follows its own trajectory calculated by the missile's onboard guidance computer. The process involves precise calculations based on orbital mechanics and Earth's rotation. Chapter 7 Hypersonic Glide Vehicle Compatibility. One of the most technologically advanced payloads associated with the Sarmat missile is the avant-garde hypersonic glide vehicle. Unlike traditional ballistic warheads that follow predictable parabolic trajectories, hypersonic glide vehicles behave differently. After initial deployment, the avant-garde vehicle re-enters the upper atmosphere and begins aerodynamic gliding at hypersonic speeds. These speeds exceed Mach 20. During glide flight, the vehicle can perform lateral maneuvers, drastically changing its path. This maneuverability makes interception by missile defense systems extremely difficult. The physics behind hypersonic glide vehicles involves a delicate balance between aerodynamic lift, atmospheric drag, and thermal protection. Chapter 8 Missile Defense Penetration. Modern missile defense systems rely on a combination of radar detection, interceptor missiles, and space-based tracking. Systems such as the ground-based mid-course defense are designed to intercept incoming warheads during the mid-course phase. However, heavy MIRV missiles like Sarmat include numerous countermeasures, including decoy warheads, radar reflective balloons, electronic jamming devices, maneuverable re-entry vehicles. These countermeasures create confusion for interceptor systems, which must distinguish real warheads from decoys traveling at extremely high velocities. Chapter 9 Strategic Deterrence Doctrine. The existence of weapons like the Sarmat missile is closely tied to the concept of mutually assured destruction. This strategic theory emerged during the Cold War and states that if two nuclear-armed powers possess enough weapons to destroy each other, neither side is likely to initiate a nuclear war. Thus, paradoxically, the presence of extremely destructive weapons can contribute to strategic stability. The Sarmat missile fits into Russia's nuclear triad, which consists of 3 delivery platforms: land-based ICBM, submarine-launched ballistic missiles, strategic bomber aircraft. Together, these systems ensure that even after a surprise attack, a nation retains the ability to retaliate. Ending narration. The future of strategic weapons. As missile technology advances, the boundaries between space science, aerodynamics, and military engineering continue to blur. Weapons like the RS-28 Sarmat are no longer simply rockets. They are complex systems integrating propulsion engineering, artificial intelligence, guidance algorithms, hypersonic aerodynamics, and advanced materials science. Yet behind every missile lies a deeper question. In a world where a single launch could change the course of human history, the ultimate purpose of such weapons may not be their destructive capability, but the fragile balance they enforce. The Sarmat missile stands as both a triumph of engineering and a stark reminder of the immense power humanity now holds.